Hello and welcome to MATLAB programming for numerical computations. We are in module 3. In the second part of this module, we have been covering numerical integration. This is the last lecture in this module. In this lecture, we will consider MATLAB functions that can be used for numerical integration. Specifically, we will take two functions, trapz and quad. We will also look at solving an application problem using numerical integration. In the previous lecture, we have considered trapezoidal rule. We have considered both the single application of trapezoidal rule as well as multiple applications of the trapezoidal rule. We wrote our own code in order to compute the integral using trapezoidal rule. Today, we are going to use a MATLAB function called trapz in order to compute that integral using the trapezoidal rule. Okay, the usage of this MATLAB function is the integral I is trapz x comma fval, where x is the independent variable and f is f calculated at those various values of x. X in this case is going to be an n+1 dimensional vector, and fval also is an n+1 dimensional vector, such that the function values fval are the values that are specified to the corresponding x values. What that means is the first guy in fval is f of x1, the second guy is f calculated at x2, third guy is f calculated at x3, so on and so forth. So let's look at the example that we took in the previous lecture and solve this using the MATLAB function trapz. So this was the script that we wrote in the previous lecture. What we did was we specified the problem statement over here. Then we used multiple applications of the trapezoidal rule and did that in two ways. The first one was to calculate trapezoidal rule by summing the from n intervals. The second way was we derived a direct formula for using the trapezoidal rule and use this as shown over here. The third way is to use the trapz function, and I will show that today using MATLAB trapz function. Okay, let's do help trapz. Okay, and if you look at the help for trapz, your integral is trapz of y if you have your x as unit spacing. That means if x is 1, 2, 3, 4 and so on up to n+1, then we can use z equal to trapz y. However, we know what our values of x are and they are not given by unit spacing. Therefore, we need to use the command z equal to trapz x comma y, where x are the independent variables and y are the corresponding values of the function. So this is exactly the usage that I have shown over here. So what we can do is we can just write that I trap3 equal to trapz x vec comma f vec using trapz function. dist I trap3 err3 will also display error 3, and let's calculate err3. err3 is ABS of trueVal minus itrap3. Let's save this and let's run this function, or let's run this script rather. Okay, we have run this and we can see using the trapz function we get the same integral value as we had gotten before, and the error that we get, that is trueVal minus the itrapz val, is also the same as before. So as you can see, it's fairly easy to implement or apply this trapz function. Okay, let us look at writing this same multi-step integral from scratch. I will say edit multi-step integral 2. Okay, redo the previous problem. I'm doing it again just for sake of clarity. A was 1, B was 2, N was, I believe, 200. Yeah, N was 200. And our function was given by this. Okay, our h was b minus a divided by n. Our x vec was a in steps of h to b. Our f vec was my fun int of x vec. Okay, and I was equal to trap z of x vec comma f vec. We just save this and run this and we will see the result. So I was 0.8863, ABS of true val minus I. You will see the error is the same. Okay, so what I've done is I've shown you how quick it is to use trap z function in order to calculate the integral using the trapezoidal rule. Okay, let's save this and let's close this function. Okay, now we have finished using the trap z function. That was the first MATLAB function that I wanted to cover in this lecture. The second function that I wanted to cover is what is known as quad. In quad, in the method quad, what we actually do is we pass on our function file itself to the MATLAB command quad. How we do that is what is known as the anonymous functions. Okay, at x means x is the variable and my fun is the file that calculates the function f of x. Okay, so the function my fun returns f of x for any given value of x. This x is specified in the brackets inside this @ sign, and the my function is the name of the file that we are going to use in order to pass on that function. Okay, this x is are the values at which we are going to calculate our integral. Okay, now using the function, this is going to be the common syntax of using any function that we are going to do pass on as an argument to a MATLAB command. Okay, so let's go to MATLAB and look at this now. I will do help function handle. Okay, function handle is obtained by giving at function name or at arg list, that means list of arguments followed by that function name. What that means is this is, let's say we want to pass on a function. What function we wanted to pass on over here? We wanted to pass on the function myFunInt, which is a function of x. The way we pass this on is at x myFunInt x. Okay, so this specifies that x is the variable that is required in the function. This is the name of the file containing the function, and this is exactly the same as this particular guy. If we have a function of two variables, say x and y, the way we will write this is myFunInt x comma y. Okay, that is how we are going to pass on the functions to MATLAB commands that are going to use these functions. Okay, the command that we are going to use in order to calculate the integral is known as quad. So let's check help quad. Okay, quad will give you the integral of a function specified in a file fun from a to b. We have our function f of x that's specified in myFun int. So at x myFun int x, that's how we are going to pass on the function handle to the command. Okay, so our I is going to be quad function name comma initial the lower bound comma the upper bound. This is how we are going to run our quad command. Our lower bound was 1, our upper bound was 2, and we run this I and we will get our integral. If we recall from what we did just a couple of minutes back, the value of integral, the true value of integral was indeed 0.8863. This is the way to use quad. What I'm going to do next is we will take up one more example, and that is going to be a physical example that we take. So what we are going to do is find this integral from 0 to 0.5 of this particular function, where the function is f by k multiplied by 1 divided by 1 minus x to the power 1.25, where f is 10, k is 5, and we want to integrate from 0 to 0.5. Okay, so let's go to MATLAB and see how we want to do that. We will create a function, edit my reactor function. Okay, function fval equal to my reactor fun of x. Okay, capital F and small k are the values that we need to give. Capital F is 10, small k is 5. Okay, and the function is f by k, fval equal to f by k, the whole thing divided by 1 minus x to the power 1.25. 1 minus x to the power 1.25. Okay, that's going to be our function. Now, how do we vectorize this function? So let's say we were expecting our x not to just be a scalar x but to be a vector x. So we want to make this into a more allow x to be a vector as well. How we are going to make this into a vectorized function? We just make a dot slash over here, because this guy is a vector, and because this guy is a vector, I will also have a dot caret over here. Okay, and I have saved this as my reactor fun. How are you going to call this particular function or pass on this function to MATLAB commands? Using at x my reactor fun x. This is going to be, this entire thing is going to be the function handle that we are going to use. So what we do is v is equal to quad this particular guy, which is basically at in bracket the variable x and followed by space and the file name with that same variable inside the brackets. So that is what it's going to be, and the limits of integral are from 0 to 0.5. So you go over here, so limits of integral are 0 to 0.5. Okay, and we press enter. And this is going to be the volume of the reactor that is required to obtain conversion of 0.5. So with that, I come to the end of this lecture. What we did in this lecture basically covered two different MATLAB commands in order to find the integral. The first one used the values of function at corresponding values of x in order to give the integral using trapezoidal rule. That function was known as trapz. The second function that we used was quad. We used the function quad in order to find the integral of any function. In using the function quad, we pass on the function handle using this particular method of passing the handle. Okay, so with that, I come to the end of this lecture and indeed to the end of this module. In module 3, we covered numerical differentiation in first 3 lectures. In that, we covered first derivatives and higher derivatives df by dx, d square f by dx squared using forward, central and backward difference formula. We also saw that there is an optimal step size for which the error is minimum. We also looked at partial differentiation, how to do that. In the second part of this module, we covered numerical integration. In lecture 3.4, we covered trapezoidal and Simpson's rule single application. We extended it to multiple application of trapezoidal rule in case we divide the overall domain into multiple intervals and apply trapezoidal rule. And finally, in today's lecture, we covered 2 MATLAB functions called trapz and quad in order to compute the integral. With that, I come to this end of this lecture and the end of this module. See you next week. Thanks and bye.